Nuclear chemistry continued. Nuclear power, fission versus fusion. Now, nuclear power comes in two main types, fission and fusion, and these use almost opposite processes, but they both produce enormous amounts of energy compared to chemical reactions that you've learned about in the other units of this course. We're going to talk about the decomposition of atomic nuclei and the recombination of atomic nuclei, and these are called fission and fusion respectively. So fission, you can think of fission as fizzing out or fizzling out of the nucleus. If you start with a large nucleus, it will sometimes split on its own into smaller nuclei, smaller, more stable nuclei, if you're starting with a very, very large nucleus. In some cases, you have to initiate that reaction by hitting the nucleus with a particle like a neutron. And these produce large amounts of energy if the starting nucleus is very large, like uranium or plutonium, those types of elements. The smaller ones in this case are more stable. And this type of reaction is used in nuclear reactors. So shown here is a neutron about to collide with the nucleus of a very large atom like uranium or plutonium. And as it collides, it initially forms this complex with the neutron and then splits into two large fragments, the fission fragments, and these are two new nuclei. These nuclei are not generally the same nuclei. Usually you get two different smaller nuclei formed from the original large nuclei, but you will also frequently get other small particles being formed like neutrons or protons. In this diagram, the gray represent neutrons, the red represent protons, and you can see that in this reaction, one neutron initiated the reaction, but the reaction produced three new neutrons in the process. And this is very common in fission reactions, and you will often see 1, 2, 3, or even 4 new neutrons being produced that can then interact with other large nuclei to split them as well. And this chain reaction can be used in nuclear reactors. Occasionally you will see a proton as a product, or more than one proton, but usually it's neutrons, but the main products are these two new nuclei. This reaction, when it's more out of control, is actually used in fission bombs, also known as atomic bombs. The original 2 atomic bombs that the United States dropped on Japan at the end of World War II were fission bombs. The first one used uranium, and the second one used plutonium. Now, fusion is essentially the opposite type of process. It's a combination of nuclei. So you start with 2 very small nuclei, or occasionally bigger ones, but that's a harder reaction to make work. But you start with 2 smaller nuclei, and you collide them together, they fuse together, and you might get a particle coming off, a small particle coming off, like a neutron shown here, or a proton occasionally, or even another small nucleus, but generally you're going to form a larger nucleus. So in this particular reaction that's playing over and over again, you're starting with tritium at the top. That's a hydrogen, it's hydrogen 3. It's a hydrogen, all hydrogens have 1 proton, and tritium has 2 neutrons in addition. Deuterium is a different type of hydrogen shown in the bottom on the left, and deuterium is hydrogen 2. It has 1 proton in red and 1 neutron. And when you collide these together, you end up producing a particle that has 2 protons, which is by definition helium, and it also has 2 neutrons, so that makes it helium-4, a total of 4 large particles in the nucleus. And in addition, this particular reaction also releases a new neutron as a side product. So these produce a large amount of energy as well. If you look per reaction, these reactions produce less energy per reaction, but because you're using such small nuclei in these reactions, the amount of energy you produce for the same amount of mass in a fusion reaction is much more energy than you would produce in a fission reaction, approximately about fourfold. And so in this case, in fusion reactions, when you're fusing together two nuclei to make a larger nucleus, the larger one is more stable. And this is used in hydrogen bombs, or what are called fusion bombs. These bombs have been around since the early 1950s. They are significantly more powerful than the atomic bombs, and they're obviously, both types of bombs are obviously quite dangerous. In addition, you'll notice that currently only fission reactions are used in nuclear reactors. There has been work for probably close to 50 years to develop nuclear reactors that use fusion reactions, but these are much, much more difficult. And the running joke in the physics field is that if you ask somebody how long before we have fusion-based nuclear reactors, they'll always tell you 20 to 30 years, and they've been saying that for the last 50 years. Though there have been some amazing advancements just this year alone. So who knows when this will be available to the public. But when it will be available, it will be an enormously useful source of energy, fairly cheap energy for the world. And this reaction is also the reaction that our sun and most stars use to generate heat. In our case, the sun is taking 4 hydrogen 1 atoms, and these are essentially protons, 4 protons, and fusing them together to make 1 helium-4 nucleus. So you're making 1 helium atom from 4 hydrogen atoms, and this is a multi-step process. It takes many steps to add these hydrogens together. It's not all in one reaction, but the sun, because of its high gravity, will squeeze the hydrogens together, forcing them to form this new helium-4 nucleus, and you'll notice 2 of the protons in the process have turned into neutrons to make this final nucleus. But a gigantic amount of energy is released, and this is why we get heat and light from our sun, as well as almost all the stars. In 1933, the famous scientist Ernest Rutherford said, the energy produced by breaking down of the atom, in other words, this fission that I just referred to, is a very poor kind of thing. Anyone who expects a source of power from the transformation of these atoms is talking moonshine. And if you remember, moonshine is the illegal alcohol that was made back in the 1930s in the United States. So in the early 1930s, no one thought that we would get energy from reactions of the atomic nucleus. They thought that was just a joke and that this would never happen. But oddly enough, a little while later, this statement was made, and I won't read the whole thing, I'll just read the red parts. In the course of the last 4 months, it has been made probable that vast amounts of power would be generated. And it's almost certain that this could be achieved in the immediate future. And this was in a letter that Albert Einstein sent to Franklin Delano Roosevelt, President of the United States, in 1939. So in only 6 short years, the science had advanced so much that the idea of getting useful energy from fission was a joke in 1933 and became a near certainty in 1939. I should point out that while Einstein is attributed with writing this letter was actually ghostwritten by other physicists, notably Leo Szilard, a Hungarian scientist, who was brilliant but not as well known in the field or to the general public as Albert Einstein. So he knew that no one would believe him, so he sent the letter to Albert Einstein, and he had help from Eugene Wigner and Edward Teller. Edward Teller is the father of the hydrogen bomb, the fusion bomb that I just mentioned. And so these gentlemen helped pen the letter. Einstein sent the letter to FDR, and this is the letter that got Franklin Delano Roosevelt thinking about starting the Manhattan Project, the project that made the first atomic bombs. So shown here is a uranium chain reaction. It's a fission chain reaction. And as I mentioned, you have to start these, or you frequently have to start these with a single neutron coming in from the left here, splitting one atom of uranium, and in the process, these each produce new neutrons as well as the split nuclei, the smaller nuclei, but these new neutrons can then interact with other uranium nuclei, and they will split those and producing more neutrons, and this can keep the chain reaction going. So a critical reaction is when you have just enough of these fissions to keep the chain reaction going at a steady rate. In other words, the amount of neutrons produced is exactly equal to the amount that are used in the reaction or escaping. In other words, you're not making an excess of neutrons. Some will escape and some will split. So you get one uranium starting another, starting another, starting another in a fairly consistent, stable pattern. And this is what is used in nuclear reactors today, the fission reactors. All nuclear power plants in the world use fission reactions. A supercritical reaction, however, is when you make too many neutrons. The neutrons are produced in excess because one way to do that is to cram the atoms together tighter so that when a neutron is released, none of them escape. They hit the next uranium, and that produces multiple neutrons, which split multiple uranium nuclei or plutonium uranium nuclei, and this just keeps the chain reaction getting faster and faster. So the rate will increase out of control. It'll be completely out of control, and we call these bombs. These are the nuclear bombs. The fission bombs are also known as the atomic bombs, the original atomic bombs. So a typical type of reaction of a fission reaction that's used both in some nuclear power plants as well as in the first atomic bomb is this one. You have a single neutron reacting with a uranium-235. Uranium-235 is not the common form of uranium. It's less than 1% of total naturally occurring uranium, so it had to be purified first. But you hit the neutron, you use the neutron to hit the uranium nucleus, and for a brief moment, you'll get the combination of these two particles, uranium-236, which has that extra neutron, but this is extraordinarily unstable and will split into two smaller nuclei. And I've shown an example where it splits into barium-141 and krypton-92 with 3 additional neutrons. And you'll notice neutrons are particles that obviously don't have any protons, so their atomic number is 0, but they do have the mass of similar to a proton, so they have a mass number of 1. And in this reaction, we produce 3 of these, plus an enormous amount of energy. And the energy might be written in units that you're not familiar with, called electron volts, and because there's so many of them, it might be in kilo or 1,000 electron volts, or more commonly, mega electron volts, millions of electron volts. And so this reaction shown here is just one of the many ways that uranium-235 can be split. In fact, there are literally dozens of ways it can be split to make many, many different types of smaller nuclei, but most of them will produce a large number of neutrons in the process. So you'll get between 2 or 3, maybe even 4 neutrons per reaction to keep the chain reaction going. So this is an example of a fission reaction, atom splitting. So when you hear the term splitting the atom, they're talking about a fission reaction. And this particular one releases 3 new neutrons to start the reaction again. All fission reactions with atoms this large will produce large amounts of energy. And in this reaction, the energy produced by splitting a single U-235 atom, or uranium-235, is approximately 200 million electron volts, or 200 MeV. We also say mega electron volts. An electron volt is a very small unit of energy, but we're only talking about one atom. If you're interested in the conversion to joules, here it is. 1 mega or million electron volts is about 1.6 times 10 to the minus 13 joules. So an incredibly tiny amount. So if you have a single atom that's making 200 MeV, that's about 3.2 times 10 to the minus 11 joules. It doesn't sound like a lot of energy, but that's a gigantic amount of energy compared to chemical reactions, reactions where we're not changing the nucleus, we're just adding atoms together or breaking bonds between atoms or forming new bonds. So for comparison purposes, if you had 1 kilogram, okay, this is about 2.2 pounds of pure uranium-235, and you were able to split all of that at once, this would produce the same amount of energy as if you exploded 20,000 tons, and remember a ton is 2,000 pounds, or about 1,000 kilograms, 20,000 tons of TNT. And this is what's known as a 20 kiloton bomb. So when you hear the term 20 kiloton or 20 megaton, they're talking about the equivalent in energy of exploding TNT, a conventional explosive, a non-nuclear explosive. So you can see that nuclear reactions produce enormous amounts of energy compared to even very high energy explosives. And for comparison purposes, in the original bomb that was dropped on Hiroshima in 1945, it had 64 kilograms of uranium-235 on it, but only 0.88 kilograms of that material, a little over 1%, actually split. So it had a very low efficiency, but that was still enough to produce 13 to 18,000 tons of TNT equivalent. So about 15 kilotons of energy, meaning it had the same energy as if you exploded 15,000 tons of TNT, this single bomb where only a portion of a kilogram actually exploded. So you can see by comparison, nuclear reactions are far more powerful than chemical reactions. So fusion, remember this is nuclear combination. You're pressing atoms, nuclei together to form larger atoms, and these produce gigantic amounts of energy as well. And the product isotope, as it turns out, doesn't have the same mass as if you combine the parts. In other words, if you add the parts together of the two nuclei that are combining, the final product actually has a little bit less mass than the starting material. You've actually lost a tiny amount of mass. And I'm not talking about losing particles. I'm talking about the mass of some particles has changed, and as a result, that mass has to go somewhere, and the mass is converted directly to energy. And we know how much energy because we have the famous expression E equals mc squared. So this tiny, tiny fraction of mass that is lost, it's essentially turned into pure energy. And because of this formula, you notice mass times the speed of light squared. C is the speed of light. We know that the speed of light is a very large number, almost 300 million meters per second. So when you multiply a small amount of mass by that big number squared, you will get a gigantic amount of energy even from a tiny amount of mass that is converted directly. And in the case of the sun takes 4 hydrogen atoms, as I mentioned, to make 1 helium atom. But if you actually, to add up the mass of 4 hydrogen atoms, and then compare that to the mass of 1 helium atom actually has a mass that's a little bit less than the mass of 4 hydrogen atoms. You've actually lost some mass. And that mass is responsible for the energy we get from the sun fusing these 4 hydrogens together. Now, I've shown here the actual pathway that our sun uses to convert 4 hydrogen atoms on the left to the 1 helium atom on the right. You are certainly not responsible for remembering these reactions. Just realize that these are pieced together 2 at a time until you end up forming the final helium. So 4 hydrogens make 1 helium and an enormous amount of energy in the process. You also get some side particles being formed, some beta particles, and some other particles we haven't talked about, like antineutrinos. They're not. They're shown here with the little symbol that looks like a V. That's the Greek letter nu. And that's actually an antiparticle. You're not responsible for that. And you also get gamma rays coming off of this, so high energy photons. This is the light that's actually produced from the sun, and it's extremely high energy when it's first produced. So you get helium made from the hydrogen, and you get enormous amounts of energy produced, and that is why we have a sun that warms our planet. Now, we're currently trying to mimic this reaction by doing simpler versions of this. And one version that is being used as probably the best archetypal version of this is to combine one hydrogen 2, that's deuterium, with one hydrogen 3, that's tritium, to make one helium 4 and one neutron. And this is the reaction I showed you in the little mini video earlier in this module. And you see that both of these two product particles, the helium that's made, and note this is not an alpha particle. Alpha particles are helium nuclei that result from a big nucleus splitting off a piece. This is a fusion reaction where you're fusing two tiny hydrogen nuclei to make one somewhat bigger helium nucleus. And that is a fusion reaction, not an alpha decay. And you also get this neutron. And both of these two particles, the helium-4 and the neutron, have significant amounts of energy because they both fly away from the original reaction site very, very fast with huge energy. And that's shown here, 3.5 mega electron volts for the helium and 14.1 mega electron volts for the neutron. So someday when we get this reaction working, we can act, even if we got the simple reaction working, we can use the ocean as our fuel source. The ocean has enormous amounts of water, obviously, and most of that water is made with normal hydrogen, hydrogen 1 and oxygen, but a fraction of the hydrogen in the water is deuterium. It's a little less than 1% is deuterium, so there's a lot of deuterium in the ocean. There's a much smaller amount of tritium, but tritium can be isolated or even made in other reactions. So once this reaction is worked out so that it can be made in a sustainable way and a chain reaction can occur over and over again to produce energy, this will be a gigantic source of energy for our planet and will presumably be very cheap. So I'm going to show you a number of practice questions with both fission reactions and fusion reactions to show you how to think about these kinds of nuclear equations. So the first one, the spontaneous fission of plutonium-240 results in the production of xenon-134, 3 neutrons, and what other isotope? So the first thing you need to do is write your starting equation, and you can put a question mark for the missing isotope. But you have to figure out what are the symbols for the plutonium-240 and the xenon-134. Well, plutonium-240, if you look it up on a periodic table, you will see that it has an atomic number of 94. So the symbol would be Pu with 94 in the bottom left, as all plutoniums would be. But this particular plutonium has a mass number or isotope number of 240. That's in the upper left-hand corner. We're producing xenon-134. Looking in the periodic table tells us that xenon has an atomic number of 54 for all isotopes of xenon, but this particular one has a mass of 134. So we have plutonium-240 is producing xenon-134 plus our unknown plus 3 neutrons. And you'll notice for the neutrons, I don't simply write N or N with a 0 charge. I show N with its atomic number on the bottom and its mass number at the top. And you may say, well, it's not an atom. Why would it have an atomic number? Well, technically it has no protons, so the atomic number is 0. And remember, mass number is the sum of the protons and the neutrons. There are no protons. There is 1 neutron. That's what it is. So the mass number, by definition, would be 1. The atomic number would, by definition, be 0. And we have 3 of these, so remember, we have to multiply everything by 3. And now we have this blank, and I've just put in the amount of energy. You don't need to know that energy. It's just there in case you're curious how much energy is produced. It's not even part of this problem, 207.1 mega electron volts. So this is a typical reaction for splitting a heavy isotope of plutonium. So how do you calculate it? Well, what you need to remember is the simple rule that the mass number, total mass number on the left side of the equation will be equal to the total mass number on the right side, and the total atomic number, the bottom numbers, will be equal to the total bottom numbers on the right side. So figuring out the mass number that's missing, you take the 240 on the left, you know the other side has to add up to 240, so you take 240 and subtract the other things from it. We subtract the 134, we subtract the 3 ones for the 3 neutrons, and that leaves us with 103 mass number. That means we know our total protons and neutrons will be 103 for this missing particle. The same equation is used for the atomic mass. We have 94 on the left. That's our total. So everything on the left, 94, must equal everything on the right, 94. Well, if we know the total on the right is 94, and that's composed of 54, an unknown number, and 3 zeros, we take 94, subtract away the 54, subtract away the 3 zeros, obviously that's just 0, and we're left with an atomic number, the number of protons, of being 40. We go back to our periodic table and we look at the atomic number of 40, and we see that corresponds to zirconium, which has a symbol of ZR. Remember, you will never, ever find mass numbers on the periodic table because every type of element has multiple isotopes, multiple mass numbers. You will only find atomic numbers on your periodic table. So now we know the mass number, we know the atomic number, we know what element it is, or we can just write the symbol, zirconium with 103, or ZR with a 103 in the upper left, a 40 in the bottom left, and we can fill in our equation to show that plutonium-240 breaks apart, or fizzes, or splits into xenon-134, zirconium-103, and 3 neutrons, plus this energy. We're not going to worry about the energy. The second problem here is fusion, so now it's the opposite process. We're combining nuclei. Fusion, we're fusing together 2 nuclei. Fusion of nitrogen-14 and a proton. Well, proton is just hydrogen-1. It's the nucleus of hydrogen-1. It's just a single proton. So what happens when we fuse these together? Well, we have to write the symbols. Nitrogen has an atomic number of 7. Hydrogen has an atomic number of 1. We write our symbols, 14 at the top, 7 at the bottom for nitrogen, 1 at the top, 1 at the bottom for hydrogen for these particular nuclei. And we simply add the tops together, we add the bottoms together. It's very straightforward. We could write the hydrogen, by the way, as either hydrogen, or we could write it as a proton. You don't have to write the positive charge. I put it there just to remind you. But the fact is, these are the same thing. A hydrogen-1 nucleus is a proton. So either way you write it is fine. Just be familiar with both ways. So we know the mass number is 15. 14 plus 1 is 15. We know the atomic number is 7 plus 1, 8. Looking at the periodic table, we see atomic number 8 is oxygen. So our product must be oxygen 15. And if we stick that back in our equation, we have nitrogen 14 plus hydrogen 1, or proton, produces in a fusion reaction oxygen 15. Here are 2 more problems. The top one, fusion of deuterium, that's hydrogen 2, and helium 3, results in the production of a single proton, so that's our extra little particle, and what isotope? In other words, that's the real fusion product. So we have to write these out. Hydrogen has an atomic number of 1, helium has an atomic number of 2, and we know the masses, 2 and 3 respectively. We know our product is a proton. I've written the amount of energy that's produced. This particular reaction produces 18.3 mega electron volts. Again, it's not important to the problem. It's just there for your information. So again, we're going to address this problem like all nuclear reactions, remembering that the sum of the mass numbers on the left must equal the sum of the mass numbers on the right, and the sum of the atomic numbers on the left must equal the sum of the atomic numbers on the right. So in this particular reaction, we know that the mass numbers on the left must equal 5. 2 plus 3 is 5, and that means that 2 plus 3 minus the 1 from the proton, that's the top number in the proton, must equal the remaining mass number, which is 4. And you'll notice I've written proton as 1 and 1. That's the same as hydrogen because a proton has a mass number of 1. It's a proton or a neutron. And it has 1 proton because it is 1 proton, so it has an atomic number of 1. Likewise, the atomic number must sum up to 3 on both sides of the equation. So we have 1 plus 2 on the left minus the 1 from the proton equals 2 remaining. And 2 remaining tells us that this element must be a helium. So in fact, we're making helium-4. And you'll notice in this reaction, we're starting with deuterium, that's hydrogen 2, and adding helium-3 to make helium-4 and a proton. So it's similar to the reaction you've seen already for fusion, but we're starting with helium-3 instead of hydrogen-3, and we're ending up with an extra proton instead of an extra neutron. So it's a different reaction, but it's very similar in terms of what's actually happening here. So if you want to write the whole equation, that would be hydrogen-2 plus helium-3 produce helium-4 plus that extra proton and a lot of energy. And don't worry about the amount of energy. It's just there to tell you energy is produced. But pretty much every nuclear reaction, not just fusion and fission, even alpha, beta, and gamma, all are associated with certain amounts of energy. It's just these, for fusion and fission, tend to be large amounts of energy, so people tend to write them down. Again, you are producing helium-4 in this particular fusion reaction. Other fusion reactions might make something different. But this helium-4 is not an alpha particle. Not an alpha particle. It is the fusion product of hydrogen-2 and helium-3 to make a bigger version of helium, helium-4, a heavier version. So don't confuse this with alpha decay. And the last example in this set, fission of uranium-236. So this is the 236 that you actually make by slamming uranium-235 with a neutron, which I'm not showing here at all. But let's say we're starting with uranium-236. The fission of this results in the production of 2 isotopes, cesium-141 and rubidium-94. And I showed you other examples of this isotope, uranium-236, splitting in different ways. This is one of the many other ways it can split. So what other particle is produced? Well, we need to write down our equation. We know uranium has an atomic number of 92. We know that cesium has an atomic number of 55, again from the periodic table, and rubidium has an atomic number of 37. We write all those numbers in with the symbols. Then we're given the mass numbers in the problem. Uranium is 236, cesium is 141, and rubidium is 94. So the numbers in the names are always the mass numbers, also known as the isotope numbers. You write your symbols, you have your blank. As always, the numbers on the top on the left must equal the numbers on the top on the right, the mass numbers. The numbers on the bottom, the atomic numbers on the left, must equal the atomic numbers on the right. So we have 236 on the top from the left side, so we know the right side must add up to 236. Well, if we subtract out the other two things we have, we would just take a calculator, type in 236, subtract out the 141, subtract out the 94, we're left with a mass number of just 1. That tells us that this is a single small particle. If we look at the atomic numbers are already balanced. There's 92 on the left, and when we subtract out 55 and 37, we're left with nothing. In other words, 55 plus 37 is also equal to 92. That means the remaining particle has no protons in it. It has a mass number of 0. I'm sorry, an atomic number of 0, but a mass number of 1. And we only know of one particle that has no protons, but still has a mass of 1, and that is a neutron. So our remaining particle product is a neutron. Uranium-236 splits by fission into cesium-141 plus rubidium-94, and the remaining product is a neutron, which is good because that neutron can then slam into other particles, helping to split those in a chain reaction. And we're going to stop here.